Continuing with the second part of section 7, still design tools, and these are circuit extraction tools we're looking at here. And basically the idea is once a layout has been produced, it's important to be able to extract electrical parameters. So this is slightly different than our design rule checking before. We were looking at geometry. Here we want to extract some electrical parameters. So the key elements that we want to try to extract would be things like the transistors, the contacts, so that we have a connection on wires, capacitances, which are largely our parasitic capacitance, as well as resistances, because we know that these are all going to impact the performance of the layout. So the algorithms that are used to identify the elements are much like those from the DRC program, and most extraction tools actually implement some type of DRC functions as well. So the circuit elements in CMOS are usually identified as follows. Well, transistors are relatively straightforward, and this occurs wherever polysilicon would cross a diffusion. That's basically the definition for the transistor. So if we were looking back at our DRC, that would be poly and diffusion, that equals a transistor. Once you have that region identified, you can identify the area, the width, and the length. And those can be all calculated, and it provides performance measures, because we need to know what the drive of the transistor is, the beta, and we also know what the load is going to be if it was a gate driving a wire, for example. It's also important to note the substrate connections. They should be recorded because those can affect the threshold voltage, and we saw before as the body effect. So circuit elements are also identified as capacitance, and that occurs between all layers. Like every time one layer crosses another, the area of that intersection should be used to calculate the capacitance. In this particular case, you'd have M1, metal 1 crossing metal 2, and where they cross, that would be a definition of a capacitor, which provides the capacitance between those two metal layers. Of course, wherever metal 1 or metal 2 is, it's also a capacitor over the substrate. But in any event, it involves estimating the area and the perimeter of all of the layer polygons. So some of the other circuit elements that we need to identify would be the resistance, and resistance occurs in all lines, and again that depends on the length and width of each line. We have to account for bendings and vias, also could be important, and these are expressed in units of ohms per square, as we saw much earlier on. Okay, so once you've done all that extraction, there are some electrical rule checkers, so it's similar to DRC, and basically they're tools to extract the layout netlist information and check for various electrical rule violations. So a few of the electrical rule violations that are commonly checked for would be things like a short circuit, so it's a net that's connected to ground or power, and those would be flagged as possible errors, or an isolated circuit, a net which is not driven by any signals or assumed to be erroneous. And you probably saw that in some of your labs as warnings when you were doing your place and route. It's also possible for electrical rule checkers to give you an estimate of what the power consumption might be, and you might ask yourself how you'd check power consumption and current in lines. And one of the techniques that you might use is, if you remember the equation we had for power dissipation, it's sort of related to the capacitance, the voltage squared, and the frequency of operation of that module, and then perhaps you would augment that with an activity function for how often that module is operating. Once you have this, you get a pretty good idea what the current is going to be, and if you know what the current is going to be, you can make sure that you're not violating a design rule that would tell you that the width of that wire should be a particular size, so that you don't violate some current density design rule. You can also extract transistor ratios, so it's possible to verify that transistor ratios are reasonable in the circuit. And remember what that means from our early analysis of our inverter. We kind of want the pull up and the pull down rise and fall times to be roughly equal. So if that isn't the case, and this is just a geometry comparison, errors could be flagged, and if there's mismatches between the NMOS and PMOS transistor sizes. And other types of errors that can be flagged here is perhaps a small transistor, which would be driving a big load. That could be long wires or lots of fan out associated with that particular transistor. Network comparison, this is relatively difficult to do. It's where you're trying to take your original circuit schematic or RTL and verify that the same circuit was produced. So it's difficult if the original circuit specification was structural and you perform some optimization during the layout, and for example here a redundant gate may have been removed. So it would be difficult to say that that would be the same structure you started with because a gate had been removed from it, although it would have the same functionality. Functional verification is where you analyze the circuit and try to find the basic logic gates and make sure that you can deduce the behavior of the circuit from that, and that can be compared to the original circuit behavior specification. and this is largely based on simulation to a large degree. Timing verification is a little bit more detailed here. The circuit is analyzed to find worst case delays, and if these don't meet the circuit specification, an error would be flagged in that case. So this is a much lower level detailed simulation where you're trying to include the timing information, which would be timing information from the given gates as well as delay that came from the layout of the circuit itself. More recently, these electrical and design rule checkers are used to improve the performance for place and route of modern FPGAs and ICs, and the idea here is if a timing violation can be identified early in the place and route process, an alternative design or implementation strategy could be employed. So typically you're doing place and route to minimize area, for example, but at the same time, if you can also do some timing verification, then you're going to be able to identify perhaps a line that may take too long to charge or discharge and violate a timing constraint. It sounds like it might be easy, but basically you're worrying about finding the longest path on a graph. The reason you think that might be easy is because you know that there are nice algorithms around for finding the shortest paths on a graph, but finding the longest path on a graph in general is much more difficult. But if it's a directed acyclic graph, then it's typically not as difficult as a general graph. Other things that you can do if the multiplier being implemented does not meet your performance specification, maybe you're not going to make a layout change to it, but you could change the type of design that you're using. In this case, maybe more pipeline stages could be utilized. So the result will be potentially greater performance and the cost will be more area. So a different technique was, although bigger, was faster. And these are basically architectural alternatives. For example, an array multiplier versus a Wallace tree multiplier might be one of your options. And again, you'd have to verify that you'd meet the timing specifications and didn't violate your area specifications when you're implementing that. I'll talk a little bit about simulation tools. You've spent a fair bit of time in the past few years doing simulation, certainly an important part of IC design. And the purpose of simulation is to determine the behavior of the design before fabrication. Circuit level simulators are those you're probably the most familiar with, and they're basically used to determine the analog waveform or characteristic of a circuit or a small number of transistors. So circuit level simulators typically have to work in conjunction with extraction tools. The extraction tools from the layout are used to produce a netlist, and that would contain all the electrical components of the circuit, including the parasitic capacitance and resistances. So the simulator then would read in the netlist information, so that's that back annotated information from layout, and produce a system of coupled nonlinear differential equations. And the solution of these equations produce a transient analysis of the circuit behavior. And those would be done numerically. Those are numerical techniques because those systems of equations would be relatively large. The most common circuit level simulator is SPICE. You've used it here many times, I'm sure, or HSPICE, PSPICE, and its variants. It stood for Simulation Program with IC Emphasis. Originally developed in the early 70s at Berkeley. It was written in Fortran, but C language versions of SPICE are available and has been ported to almost every type of computer. And at this point in time, we'll take a break.